Over the last 2 decades, the modern home has transitioned from a biologically quiet environment into a dense, invisible web of overlapping microwave frequencies. While the telecom industry insists this non-ionizing radiation is harmless, highly self-sufficient off-grid communities and biohackers are spending thousands of US dollars to physically block these frequencies, treating ambient Wi-Fi not as a convenience, but as a structural pollutant. A handheld spectrum analyzer sweeps across the living room, its display lighting up with sharp peaks and shifting bands. The baseline noise floor sits low, but two distinct clusters erupt above it. One centered at 2.4 GHz, another at 5.2 GHz. These are not theoretical signals. They are the continuous output of household Wi-Fi, pulsing through the air at all hours. Each spike on the screen corresponds to a specific device: the router in the hallway, a smart thermostat, a neighbor's access point leaking through the wall. The analyzer's frequency span stretches from 0 to 6 GHz, capturing not only Wi-Fi, but also emissions from smart meters and Bluetooth peripherals. The decibel milliwatts scale on the vertical axis quantifies real power, translating invisible energy into numbers: minus 40 decibel milliwatts near the router, minus 50 decibel milliwatts at the far wall, with ambient peaks flickering as new packets transmit. This is not a clean spectrum. Instead, the analyzer reveals a crowded field, dual-band Wi-Fi signals overlapping, smart meter bursts registering as brief jumps, and sporadic noise from a cellular handset on standby. In a single sweep, the room is exposed as a relay station, saturated by overlapping microwave frequencies. The invisible web is rendered tangible, continuous, measurable, and inescapable. The raw data offers no comfort, just evidence that the modern home is a live environment of persistent radio frequency radiation, with every device contributing its own signature to the spectrum. A modern home runs on a network of emitters, each broadcasting in the microwave band. The inventory begins with the Wi-Fi router operating at 2.4 GHz and 5 GHz, followed closely by smart meters, Bluetooth speakers, wireless printers, cordless phones, and cellular handsets. Baby monitors, smart thermostats, and some kitchen appliances add to the constant broadcast. Each device is a registered source of radio frequency radiation, contributing to the overlapping peaks seen on any calibrated spectrum analyzer. Measurement discipline is not optional. Dr. Joel Moskowitz at UC Berkeley cautions that field meter placement, background subtraction, and averaging over minutes are required before any health claim can be made. The protocol demands a standardized approach. Meters must be set to average over at least 10 seconds. Readings logged at fixed intervals, and distances from sources measured precisely, typically at 0.5 meters, 1 meter, and 3 meters. Only then can the raw dBm, or microwatts per square centimeter readings, be compared to regulatory thresholds. The public exposure limit, as defined by FCC and ICNIRP, is 10 watts per square meter for the 200 to 300 GHz band. In practice, household readings are orders of magnitude lower, with Wi-Fi routers at a meter's distance, rarely exceeding 5 microwatts per square centimeter, while smart meters on an exterior wall average below 0.2 microwatts per square centimeter indoors. Still, the cumulative effect of dozens of emitters, each running on its own schedule, creates a persistent ambient load. To ensure data integrity, the measurement protocol is treated as a pledge. All sources are identified, meters are calibrated, and logs are kept in units that match regulatory standards. This approach grounds the investigation in reproducible physics, setting the stage for direct, hardware-based experiments that translate abstract numbers into actionable change. A calibrated field meter is positioned just 2 inches from a powered Wi-Fi router. The digital readout spikes, registering a dense field at 2.4 gigahertz. Power density at this range sits near 1 microwatt per square centimeter, a value that dwarfs the ambient background. Now the router is moved to the far end of the room, exactly 10 feet away. The meter's numbers collapse, falling to roughly 0.03 microwatts per square centimeter. This is not a subtle drop. The reduction is a factor of 3,721, expressed in decibels as minus 35.7 decibels. The physics is absolute. Every time the distance increases by a factor of 60, the field intensity falls by 60 squared. That is 60 times 60. The inverse square law governs all point source radiation, from router antennas to smart meters. In practical terms, a device pressed against the body produces thousands of times more exposure than the same device across the room. The field meter, held steady, turns abstract math into physical evidence. Decibels are not just numbers, they are ratios, each 10 decibel step marking a 10-fold change in power. The live demonstration locks the 35.7 decibel figure in memory. A single measured action wipes out over 99% of the original exposure. This is the baseline for all physical interventions. Distance is the simplest, most powerful tool. No filter, shield, or paint can match the raw effectiveness of moving a transmitter further away. The numbers on the meter do not lie. They show the invisible world of household microwave radiation obeys strict, predictable laws. Laws that can be measured, repeated, and used to engineer a safer, quieter home. A mechanical timer, priced under $5 at any hardware store, plugs directly into the router's power supply. The timer's dial is set so that power is cut for 8 hours each night, aligning with typical sleep cycles. This simple intervention transforms a continuous transmitter into a part-time device. A calibrated field meter logs the average power density in the main bedroom before and after installation, with readings integrated over a full 24-hour cycle. Prior to the timer, the meter records an average of 5 microwatts per square centimeter at 1 meter from the router, which is consistent with the expected output of a dual-band consumer unit running at full duty. After the timer is installed and programmed for nightly shutoff, the same meter in the same position logs an average of 0.8 microwatts per square centimeter. The reduction is not theoretical. Over the course of a week, the time averaged exposure drops by 84%. The router remains fully functional during waking hours, with no loss of connectivity or performance. The only change is the absence of microwave radiation during the hours when the body is most vulnerable to environmental stressors. This approach requires no technical skill, no rewiring, and no sacrifice of modern convenience. The analog timer stands as a physical, measurable break in the wireless grid, a hardware-based act of digital hygiene that slashes exposure by nearly an order of magnitude. The data, logged and reproducible, confirm that duty cycle reduction is a practical, cost-effective remedy within reach of any household. A hardwired Category 6 network begins with a plan and a bill of materials. The goal is absolute: eliminate airborne data transmission and replace it with shielded copper. The inventory is precise: 100 feet of shielded Category 6 cable, 2 shielded RJ45 connectors, a metal wall plate, a shielded keystone jack, a section of conduit, a grounding bar, and a shared patch panel slot. The total cost, including 2 hours of skilled labor, is $147.10, itemized down to the last cent. Each component serves a physical function. The cable itself is 23 AWG solid copper, wrapped in foil and a braided shield to reject external fields. The connectors are metal-clad, terminating the braid at both ends. The keystone jack anchors the shield to a grounded metal plate, and the patch panel consolidates every run in a single bonded chassis. Installation is a matter of physics and discipline. The pathway is mapped through a crawl space or along an interior wall. Conduit is cut and anchored to avoid sharp bends. The cable is pulled, jacket stripped, and the exposed braid is wrapped around a short length of copper foil, forming a drain pigtail. Each RJ45 is crimped so the shield makes direct contact with the connector shell. At the panel, the drain wire is screwed to a low impedance copper bar, itself bonded to the building's electrical ground. This single point ground prevents circulating currents and ensures any stray radio frequency energy is shunted safely away. Every connection is tested with a network analyzer. No open pairs, no ground loops, and no packet loss. Performance is immediate and quantifiable. Where wireless delivered 120 megabits per second with packet loss and variable latency, the shielded Category 6 run achieves 940 megabits per second, nearly the full theoretical gigabit. Latency drops below 1 millisecond. Packet loss is functionally zero. The spectrum analyzer, swept across the room, now registers only a flat noise floor. No 2.4 GHz peaks, and no 5 GHz peaks. No intermittent bursts. The wireless grid is silenced. The home's data moves through copper, not air. The shielded run is not just a cable. It is the physical boundary between ambient radiation and a closed, measurable system. For $147.10, the invisible relay station is dismantled, and the architecture of the home reverts to a state of electromagnetic quiet. A standard bedroom, 12 by 12 feet, becomes the test chamber for architectural shielding. The first intervention is copper mesh, stapled and taped with conductive seams across drywall and ceiling. Every joint is sealed, every seam grounded to a single copper strap. The installation follows EMC laboratory protocol. No gaps wider than a millimeter. Mesh aperture kept below 1/10 the wavelength at 2.4 GHz. The material cost for full coverage lands near $1,440 for mesh and tape, with labor bringing the total to approximately $1,540. When measured with a calibrated NARDA broadband probe, ambient Wi-Fi at 2.4 GHz, previously peaking at 3 microwatts per square centimeter, drops below 0.08. The reduction is not theoretical. The spectrum analyzer records a 30 decibel drop, down to 1/1000th of the incident field. This matches the insertion loss measured in accredited EMC labs, where copper mesh routinely delivers 30 decibel attenuation at Wi-Fi frequencies. Dr. Ingrid Lindgren, an EMC laboratory engineer, confirms that a 30 decibel shield reduces a 2.4 GHz field to 0.1% of the incident power, enough to bring Wi-Fi levels below typical urban background. A second method, carbon-based conductive paint, is applied in 2 coats over primed walls. The datasheet for a leading brand specifies 22 decibel of shielding effectiveness at 2.4 GHz, with each coat adding measurable attenuation. The cost for a full room, paint, tape, grounding hardware, and labor totals roughly $2,260. Laboratory testing by Intertek and ETS Lindgren confirms the manufacturer claim. 2 coats of paint, properly cured and grounded, cut Wi-Fi fields by a factor of 160, translating to a 22 decibel drop. The field meter positioned at the head of the bed registers a new baseline. Ambient power density falls from 2.5 to 0.1 microwatts per square centimeter. The numbers are logged. The protocol repeated for 5 GHz with similar results, though attenuation at higher frequencies trends 2 to 4 decibels lower. Both interventions produce a measurable quiet zone. The difference is not subtle. Where the unshielded room acted as a relay for external and internal RF, the shielded enclosure becomes a controlled environment. The spectrum analyzer shows only a flat noise floor, interrupted by brief, low-level spikes from external sources. The cost per room, whether mesh or paint, falls within the $1,500 to $2,300 range, well above the $300 to $500 figure quoted in some DIY guides, but supported by every independent lab test. The result is decisive: a properly shielded bedroom, verified by a calibrated meter, delivers a 20 to 30 decibel reduction in Wi-Fi and smart meter exposure. The numbers are not estimates. They are measured, reproducible, and traceable to international standards. The home, once an open relay, is now a physical sanctuary, its boundaries defined not by drywall, but by engineered, validated attenuation. A smart meter on the exterior wall transmits microwave bursts at 900 MHz and 2.4 GHz, its antenna pointed outward but radiating into the home as well. Field measurements with a calibrated radio frequency meter show indoor peaks reaching 23 microwatts per square centimeter at 2.4 GHz during active transmission, levels on par with a Wi-Fi router pressed against the wall. The directional nature of the antenna means most energy is projected away from the house, but a measurable fraction leaks inside, especially in rooms sharing a wall with the meter. A simple hardware-based intervention addresses this exposure: a galvanized steel or aluminum plate, mounted with a 2 cm AIR gap between the plate and the meter's interior-facing surface. This geometry is not arbitrary. The air gap preserves the antenna's tuning and prevents detuning that could disrupt utility telemetry. Field tests confirm the effect. With the plate in place, measured power density drops from 23 to 2.1 microwatts per square centimeter at 2.4 GHz, a reduction of 15 decibels, or roughly 97% of the original field. At 900 MHz, the drop is nearly identical, falling from 6 to 1.1 microwatts per square centimeter. The attenuation is directional, sharply reducing the field entering the home while leaving external communication intact. Installation is straightforward. The plate is secured to the wall studs, never touching the meter housing itself, and grounded to the building's electrical system to further suppress stray fields. Total material cost averages under $70, with installation requiring less than an hour. The legal boundary is clear: the shield must not block the meter's optical port or interfere with data collection. Utilities permit non-intrusive shielding, but any disruption to wireless reporting can trigger a removal notice. In 2022, a homeowner in California received a formal warning after a shield caused loss of telemetry. The issue was resolved by switching to a utility-approved radio frequency absorbing foam that preserved both attenuation and compliance. The shield plate stands as a measured legal intervention, one that turns a persistent radio frequency emitter into a manageable source, confirmed by reproducible instrumented data. A farmhouse in Lancaster County, Pennsylvania, stands as a working example of a zero wireless environment. The backbone of its network is not radio frequency, but copper, over 1,200 feet of shielded twisted pair cable, routed underground through PVC conduit, and terminated in every room. The total investment for materials and labor reaches $2,500, covering cable, shielded jacks, patch panels, and 2 days of skilled installation. Each run is grounded at a central bar, ensuring any stray current is shunted safely to earth. Post-installation, a NARDA broadband field meter sweeps the interior. The display remains flat, never rising above 0.05 microwatts per square centimeter, even at points directly above the cable runs or adjacent to wall plates. This reading sits below the ambient outdoor baseline and far beneath the levels measured in homes with active Wi-Fi or smart meters. The absence of microwave peaks is not a quirk of the meter, but a reproducible result, confirmed by spot checks in the kitchen, bedrooms, and utility rooms. The data log is unbroken, no transient spikes, no drifting background, just a persistent electromagnetic quiet that matches the theoretical expectation for a fully shielded, hardwired system. Daily life in the house is not defined by deprivation, but by deliberate design. Internet access is distributed through gigabit switches, with no need for wireless repeaters or extenders. Farm automation systems, from lighting controls to data loggers, operate over copper lines. The livestock barn, linked by a buried trunk, reports sensor data without emitting a single microwatt of airborne radio frequency. No drop in productivity is observed. The network supports streaming, remote work, and precision agriculture. For the residents, the absence of wireless is not a sacrifice, but a baseline, proof that a high-functioning modern home can exist entirely outside the invisible grid. The numbers, less than or equal to 0.05 microwatts per square centimeter, are not just a technical achievement, but a statement of autonomy, measured and logged in real time. Right now, every home radiates with 2.4 gigahertz and 5 gigahertz signals, an invisible, measurable broadcast. The inverse square law remains physics, not opinion. Doubling your distance reduces the load to 1/4. For under $500, copper mesh, shielded Cat 6 cable, and analog router timers can transform a relay station into a refuge. In an era of always-on wireless, the true act of rebellion is building a closed system and measuring the difference. Share your solutions below.